Welcome to the We Will Overcome presentation series organized by the Department of Physics, Sacred Heart College, Thevara. This program is organized under the guidance of Dr. Pius Augustine, Assistant Professor, Department of Physics. This lecture will be presented by myself, Donna Treasa S, a final year BSc Physics student from Sacred Heart College, Thevara. The topic presented is Modes of Heat Transfer and Heat Exchangers. This presentation is divided into 3 lectures consisting of a total of 5 topics. In the previous lecture, my fellow group members discussed what is heat transfer and what are the 3 modes of heat transfer. Then they also discussed on what is conduction and convection. In this lecture, we will be going into the details of radiation. In this lecture, we will be seeing the definition and concepts of radiation, what are radiation properties, what is black body, and some of the laws which are associated with radiation, the spectral distribution of radiant energy, and applications of thermal radiation. Okay, so far we have seen the first 2 modes of heat transfer, that is conduction and convection. Now let us see the third mode of heat transfer, radiation. What is thermal radiation? Thermal radiation is defined as the transfer of heat from hot to a cold body without much heating of the intervening medium. Let me explain this point using an example. Suppose that we are organizing a college or school trip and we are organizing a campfire. All the students are seated around this fire a few meters away. So when we learned about convection, we learned that the air which is in direct contact with the fire gets heated up and its temperature increases. As the temperature increases, it also becomes less denser. So this less denser air tends to move up, creating a gap which will be filled by more denser air, that is the cooler air. So we understand that the region around the fire is actually filled by cooler air. But even if that is the case, students who are seated a few meters away from the fire also feel the warmth of the fire. This observation is actually attributed to radiation. Hope you understand the first point. Now the second point is that for thermal radiation to occur, an intervening medium is not necessary. This is the case with solar radiation, and we will be explaining this point in the part where we explain the applications. So the third point is that radiation is electromagnetic in nature, just like light. It also exhibits reflection, refraction, interference, diffraction and polarization, which are also exhibited by light. Regarding the spectral distribution of thermal radiation, it is within infrared, visible and some parts of ultraviolet region. To be more precise, its wavelength extends from 0.1 micrometer to 100 micrometer. One of the most important point is that thermal radiation varies with temperature, that is the intensity, wavelength and rate of emission changes with temperature. Let me illustrate it using an example. You might have seen a blacksmith heating an iron piece in a furnace. When you closely examine, you can see that initially the iron piece will be having a red color, which is some sort of light red color. So upon further heating, its temperature increases and there is a change in color from red to yellowish red color. And again, if it is heated to much higher temperature, you can see that this iron piece becomes white in color. So here you can understand that with the change in temperature, there is a change in color associated with the change in wavelength. So I hope you understand the last point which we discussed in the previous slide. Now let us see some of the terms and quantities that are used to express the radiative properties of a body. The first one is total energy density, represented by U. before going into the details, there is something else you should understand. When a thermal radiation is emitted by a body, there is a collection of waves having different wavelengths. So, total energy density is defined as the total energy for all wavelengths per unit volume. Its SI unit is Joule meter raised to -3. Second one is spectral energy density represented by U subscript lambda. It is defined as the energy per unit volume per unit wavelength. So U is meant for all wavelengths and U lambda is meant for a unit wavelength. So there is also a relationship between U lambda and U, which will be explained now. If U lambda D lambda represents the energy per unit volume in the wavelength range lambda to lambda plus D lambda, then upon integrating this term from 0 to infinity, you get U. That is, U is equal to integral 0 to infinity. 0 to infinity represents all the wavelengths. U lambda D lambda gives U. Now the third one is emissivity. Emissivity represented by E is also known as total emissive power. So this quantity power has been introduced to you since your school days. So when you hear this name power, it should automatically strike that this has something to do with energy per unit time. So let us see what is emissivity is. Emissivity is defined as the total radiant energy emitted for all wavelengths per second per unit surface area. Its SI unit is Joule meter raised to -2 second raised to -1, which can also be written as watt meter raised to -2. Now the fourth one is spectral emissivity represented by E subscript lambda. Just like the previous case, there is also a relationship between emissivity and spectral emissivity. Spectral emissivity is the radiant energy per unit range of wavelength. So here it is for unit range of wavelength and emissivity is meant for all wavelengths. Also, just like the previous case, there is a relationship connecting E and E lambda, which can be understood as follows. E lambda D lambda is the radiant energy per unit surface area per second in the wavelength range lambda to lambda plus D lambda. Upon integrating this term from 0 to infinity, we get E. The relationship is given at the bottom. So that is what is meant by emissivity and spectral emissivity. Now the fifth one is spectral absorptivity. So far we have been seeing about emission, thermal radiation emission, and now we are going to see a term which is related to absorption. So it is defined as the fraction of incident radiation absorbed by a body for a wavelength. Since A lambda is a fraction, it has no unit. Just like refractive index is a fraction, so it's something, this is also a quantity like that, it is also a fraction, so it does not have any unit. If A lambda equal to 1, it is a black body. We'll be seeing what is a black body in the upcoming slide. Now let us see one of the theories of heat exchanges. Prior to 1792, Pierre-Prévost suggested the Prévost theory of exchanges. During the olden times, people believed that hot bodies emitted hot radiations and cold bodies emitted cold radiations. But Prévost suggested that there is no such thing as hot radiations and cold radiations. He asserted that every body absorbs and emits radiations whose rate depends solely on the surface and temperature. As I said before, radiation has electromagnetic properties like light. Just like light exerts a finite pressure, radiation also exerts a finite pressure which is known as radiation pressure. It is denoted by P and the relation is given as P is equal to I by C, where I is the intensity of radiation. Intensity of radiation is defined as the radiant energy incident per second per unit surface area held normal to the direction. Here C is the velocity of light in vacuum. Now we come to radiation properties. When a radiation is incident on a body, it is partially reflected, partially absorbed and partially transmitted all at the same time. if we denote reflectivity, which is the fraction of incident radiation reflected, by rho, and absorptivity as alpha and transmissivity as tau, then we get a mathematical relation such that rho plus alpha plus tau equal to 1. For most solids, they do not transmit radiation, that is, transmissivity is equal to 0. It can be approximated as 0. Therefore, the previous relation takes the form rho plus alpha equal to 0. Now we have come to one of the most important topics in radiation, that is black body. A black body is a body which absorbs or emits all radiations falling on it. It is independent of the wavelength, that is, the thermal radiation absorbed or emitted is independent of the wavelength of the incident radiation. As the name itself suggests, black body is black in color. The idea of a black body is actually hypothetical or ideal, that is, we cannot find a body which has 100% absorptivity or 100% emissivity. The nearest approximation to black body so far obtained is lamp black and platinum black. In this slide, I have included the images of a Ferri's black body absorber and a Ferri's black body emitter. Now we shall see the dependence of black body radiation and temperature. The radiation emitted by a black body is known as black body radiation. As I said before, it is a body which absorbs and emits all wavelengths. The radiation emitter or absorbed is independent of the surface properties of the body. It is only dependent on the temperature to which the body is raised. We shall see some of the laws which can be applied to calculate the emissivity or absorptivity of a body. The first among them is Kirchhoff's law. It states that the ratio of spectral emissive power E lambda to the spectral absorptivity A lambda for a particular wavelength lambda is the same for all bodies at the same temperature and is equal to the emissive power of perfectly black body at that temperature. Mathematically, it can be written as small e lambda by A lambda equal to capital E lambda. Here, small e lambda represents the spectral emissive power, A lambda represents spectral absorptivity, and capital E lambda represents the emissive power of a perfectly black body at the same temperature for the same wavelength. The second one is Stefan-Boltzmann law. According to Stefan's law, the energy density E is directly proportional to the fourth power of temperature T. Mathematically, E is equal to sigma T raised to 4, where sigma is known as Stefan's constant, whose value is 5.672 into 10 raised to minus 8 joule, meter raised to minus 2, Kelvin raised to minus 4, second raised to minus 1. In Stefan's law, the net heat loss or gain is not considered. That is, when a body is placed in a system, it naturally interacts with the system and the surroundings, and there is actually a net heat loss or gain. In Stefan's law, it only considers the heat which is emitted or absorbed by the body. But in Stefan-Boltzmann law, the net heat loss or gain is considered. So the previous equation is written as E is equal to sigma T raised to 4 minus T naught raised to 4. It must be noted that both these equations, that is E is equal to sigma T raised to 4 and E is equal to sigma T raised to 4 minus T naught raised to 4, can be considered only for black body. If the emissivity of a body is E, then the previous equation can be written as E is equal to small e sigma T raised to 4 minus T naught raised to 4. Using this equation, you can calculate the energy density of any body. Now we shall see the spectral distribution of radiant energy. The spectral distribution of radiant energy can be analyzed by plotting a graph between du by d lambda along y-axis and wavelength lambda along the x-axis. We get different curves corresponding to different values of temperature as shown in the graph here. Based on the graph obtained, we arrive at certain conclusions which are listed here. The first one is that for a wavelength lambda, u lambda is directly proportional to T. You can see that with the rise in temperature, there is an increase in the value of du by d lambda. This clearly indicates that there is an increase in u lambda with increase in temperature. So this is the first conclusion. Now, the second one is that for each temperature T, there is a lambda max. You can see from the graph here, for 8000 Kelvin, the value of du by d lambda is maximum here. The peak is here. So this corresponds to a wavelength somewhat here, and this wavelength is known as lambda max. And for 5800 Kelvin, you have it somewhere like here, and for 4000 Kelvin also it is a different value. Third one, lambda max shifts to lower lambda with temperature. It is quite obvious from the graph here. And the fourth one is that as lambda tends to infinity or lambda tends to 0, the energy density tends to 0. On either side of the lambda max value, we can see that it is decreasing. Du by d lambda is decreasing and it reaches 0 here. You can see it reaches here 0 here, and also it is tending towards 0 here. So this is what is meant by the fourth conclusion. To explain the spectral distribution of radiant energy, certain laws were proposed and their relationships were derived. So one such law is Wien's displacement law, which is also known as Wien's law. It states that the wavelength of radiation corresponding to maximum energy is displaced as temperature changes so that the product lambda T remains constant. Lambda max T is equal to constant, or lambda max directly proportional to 1 by T, or lambda max is inversely proportional to T. So this is the mathematical relation. The second one is Rayleigh-Jean's law. According to this law, the energy distribution is given by E lambda d lambda equal to 8 pi kt lambda raised to 4 d lambda, where k is the Boltzmann constant whose value is 1.38 into 10 raised to minus 23 meter square kilogram second raised to minus 2 Kelvin raised to minus 1. Unfortunately, Rayleigh-Jean's law couldn't explain the spectral distribution of thermal radiation completely. This is because as lambda tends to 0, the value of E lambda d lambda tends to infinity, which is not in accordance with the experimental results. So, Rayleigh-Jean's law could only partially explain the spectral distribution of thermal radiation. The failure of Rayleigh-Jean's law to successfully explain the spectral radiation is known as ultraviolet catastrophe. This failure was successfully overcome by Planck's radiation law. In this law, Max Planck incorporated the quantum theory to arrive at the equation E lambda d lambda equal to 8 pi hc by lambda raised to 5 e raised to hc by lambda kt minus 1. Here, h stands for Planck's constant, whose value is 6.626 into 10 raised to minus 34 meter square kilogram per second. This law could successfully explain the experimentally observed energy distribution. So far, we have seen the definition, certain quantities and some laws associated with thermal radiation. Now, we shall look into the applications of thermal radiation. The first one is white clothes are preferred in summer and black in winter. Cooking utensils are blackened at the bottom. Hot water pipes and radiators are painted black. Polished reflectors are used in electric heaters. All these four applications are based on the fact that black color absorbs more heat energy. Now the fifth one is solar radiation, which I had already mentioned in the first slide. Let me explain this point here. We had seen that radiation does not require an intervening medium. We know that in solar system, between Earth and Sun, there is no intervening medium. But then the rays from Sun manages to reach the surface of the Earth. If there is no intervening medium, then the mode of heat transfer by which the radiation from Sun can reach the Earth's surface is only through radiation. So that is what is meant by the fifth one. We have learned all the three modes of heat transfer: conduction, convection and radiation. We shall look into the differences between all the three modes of heat transfer. First is conduction, second is convection and third is radiation. The first difference is that heat transfer in conduction is between objects by direct contact. In convection, heat transfer is within the fluid. In radiation, heat transfer occurs through electromagnetic waves. Second one, conduction is due to the difference in temperature while convection is due to the difference in density. In radiation, it occurs in all objects with a temperature greater than absolute 0 Kelvin. Regarding the rates at which conduction, convection and radiation occur, conduction is the slowest, convection is a little bit faster than conduction and radiation is the fastest. The faster occurrence of radiation is attributed to the fact that electromagnetic waves travel in air approximately with the velocity equal to velocity of light in vacuum. Now, the final difference is that conduction and convection does not follow the law of reflection and refraction. But as radiation has electromagnetic properties, it follows the laws of reflection, refraction, polarization, etc. In this slide, I have given the references which I used to prepare my presentation. You can also use these books for further reading. With this, we come to the end of the lecture on modes of heat transfer. In the next lecture, we will be seeing what is heat exchangers and their characteristics, which will be handled by my fellow group members. So at this point, I would like to thank Dr. Pius Augustine and the Department of Physics, Sacred Heart College, Thevara for this wonderful opportunity. Also, I would like to thank all of you who have been listening to my lecture with patience. Thank you all.